Welcome to the KN3 lesson, Projectile Motion. You need your booklet to take the notes. Before we begin, I recommend you look at this YouTube video as an introduction. I've got the web address there. You could click on that if we were in class, but you're probably going to have to go open up YouTube and type in projectile motion and parabolas dash science of NFL football. So projectile motion involves two kinematics equations that occur simultaneously. In the horizontal direction, the object travels at a constant speed, so we will always use the formula V average equals d over t. In the vertical direction, the velocity is affected by acceleration due to gravity, so there's always an initial and a final velocity in our variables, and acceleration always equals 9.80 meters per second squared down. Now I want you to take a look at the two following links. Again, open up YouTube. You can type in conceptual physics projectile motion, and then type in the classic bullet projectile motion experiment. You'll know you're on the right link because I also included a little picture of what the video looks like. Example 1, a beanbag is thrown from a window 10 meters above the ground with an initial horizontal velocity of 3 meters per second. We're asked how long will it take the beanbag to hit the ground. So we're going to start by making our variable list. First with the x-axis. And the x-axis, we always have v, d, and t because we said in the x-axis, the object always travels at a constant speed. So we're going to be using the formula v equals d over t in the x-axis. And that is the only formula that we use in the x-axis. We also have to do our y-axis variables. And we said that gravity is always equal to 9.80 meters per second squared down. So that is our acceleration. We also have an initial velocity, a final velocity, and there's going to be a displacement at a time. So every question, this is how we started off, by writing down our variable list just like this, with acceleration being 9.80 meters per second squared in the down direction, and we will try to fill in the rest of the variables. So let's take a look at the question and see what it has given us. It says the beanbag is thrown from a window that is 10 meters above the ground. That is a displacement in the y-axis, so my displacement in the y is 10.0 meters down. It has an initial horizontal velocity of 3 meters per second, so it's traveling 3.0 meters per second in the x direction, so that is going to be my velocity in the x direction. And it says that it is traveling horizontally. It is not traveling vertically at all to begin with, so the initial velocity in the y direction is 0 meters per second. Now, we don't know how far this thing is going to travel in the x direction, so that is unknown. We don't know how fast it's going to be traveling when it hits the ground. In the y direction, we know it's starting at 0, but we know it's going to be accelerating at 9.80 meters per second squared down, so we don't know how fast in the y direction it will hit the ground. We also don't know how long it will take for the beanbag to hit the ground. And the time is the same in the x-axis as it is in the y-axis. So where to begin? Let's take a look at what we've been given, and then we can determine what variables we can solve for. In the x-axis, we've been given velocity, but we don't know displacement in time, and we can't solve for either one of those if we only know one of the three variables. In the y-axis, I've got acceleration, initial velocity, and displacement. I can solve for time using d equals vit plus half at squared, because I know 3 of the 4 variables, so I can solve for the 4th variable. Now, typically, I wouldn't want to use this if I'm solving for time, probably, because it will give me a t squared term, a t term, and a non-t term, which means I probably will wind up going to the quadratic equation. But check this out. This is pretty cool. Initial velocity is equal to 0. So initial velocity multiplied by time, anything multiplied by 0 is equal to 0, so VIT equals 0. So that means half at squared is being added to 0, which means it equals half at squared. So displacement now equals half at squared in this situation. That's going to make things a lot easier. Now I have to isolate t. First thing I do is multiply both sides by 2, and the 2 and the half will factor out. So now I have 2d equals at squared. Now to get t squared by itself, I will divide both sides by acceleration, and they'll factor out. Now I have t squared equals 2d over a, and then to get t by itself, I will square root both sides. So t equals the square root of 2d over a. Now I can substitute my numbers in. So time equals square root of 2 multiplied by 10 divided by 9.80 meters per second squared. Now we're taking the square root of all that stuff. So you will want to make sure on your calculator you've got an opening and closing bracket at the very beginning of the square root sign and at the very end of the square root sign. So that we're taking the square root of all of this. And that gives us 1.42857 seconds. 3 significant figures because all we've done here is multiplication division, and the 10.0 has 3 sig figs, and the 9.80 has 3 significant figures, so our time will have 3 significant figures. So our time is 1.43 seconds. Now we can add that to our variable list, but I'm not going to put in 1.43 seconds. I'm going to make sure that I use those pre-rounded numbers because I'm going to wind up using time most likely in another calculation, and I only round when I get to my final answer. Right, now for part B. How far will the beanbag travel horizontally? So I'm looking for distance in the x-axis. And now since I have time, I can use v equals d over t. To get d by itself, I'll multiply both sides by t. The t's will factor out. D is equal to time multiplied by the velocity in the x-axis. So d equals 1.42857 seconds multiplied by 3 meters per second. That gives me 4.29 meters. So my answer is 4.3 meters. A soccer player running on a level field kicks the ball 9.4 meters per second at an angle 40 degrees from the horizontal. How long is the ball in the air? We said in the x-axis we always have 3 variables. That's velocity, displacement, and time. In the y-axis we always have 5 variables. That's acceleration, initial velocity, final velocity, displacement, and time. And we said that in the y-axis, acceleration is always equal to 9.80 meters per second squared down. Now let's look at the question and see if we can add more to our variable list. The ball was kicked 9.4 meters per second, 40 degrees from the horizontal. So that 9.4 has a x-axis and a y-axis component. In the x-axis, compared to the angle that we've been given, the 40 degrees, the x-axis component is the adjacent side. 9.4 meters per second is the hypotenuse. The x-axis component is the adjacent side. So the value of the adjacent side is 9.4 cos of 40 degrees, and that's meters per second. The component in the y-axis is the opposite side to the 40 degrees. So the value, initial velocity in the y, is 9.4 sine 40 degrees meters per second. Now, since the ball is returning to its original height, it spent half its time going up, half its time going down. The velocity with which it went up will equal the velocity with which it is coming back down. So the final velocity is going to be 9.4 sine 40 meter per second down. Again, that is only true because the ball is returning to its original height. And since the ball is returning to its original height, that means that the displacement in the y-axis is going to be equal to 0. Now what we do not know is how far the ball traveled in the x-axis. We also do not know how long the ball was in the air. Before I move on from my variable list, I see that in the y-axis I have 2 directions as down, 1 direction as up. So I want to switch them so they're all the same. So I'm going to change my initial velocity from positive 9.4 sine 40 degrees meters per second up to negative 9.4 sine 40 meters per second down. How long is the ball in the air? That means I'm looking for time. I will not be able to solve it using the variables in the x-axis because I only know one of the three variables. But in the y-axis, I know acceleration, initial velocity, final velocity, and displacement. So that means there's probably more than one way that I could solve for time. The method I'm going to use might be different than what you may use. The important thing is we both wind up with the same answer in the end. I'm going to use acceleration equals change in velocity divided by time. I'm going to substitute in for change in velocity, Vf subtract Vi. Now I want to isolate time. So I need to get time out of the denominator. So I'll multiply both sides by time. On the right-hand side, time will factor out. I now have time multiplied by acceleration equals Vf subtract Vi. To get time by itself, I will divide both sides by acceleration. Acceleration on the left-hand side will factor out, and time has now been isolated. So I will substitute my numbers in. The next step is punching 9.4 sine 40 degrees into my calculator. And that gives me 6.0422 meters per second with two significant figures because 9.4 had two significant figures. Notice that 6.0422 is being added to 6.0422, and that's because in the previous step, we were subtracting a negative, and subtracting a negative will turn it into a positive sign. Now, when I add 6.0422 to 6.0422, it is good to one decimal place. And following the rules of significant figures, that means my answer is then good to one decimal place. So in the numerator, I wind up with 12.0844 with now three significant figures. I'll divide that number by 9.80, which also has three significant figures, so my answer has three significant figures. 1.2331 seconds becomes 1.23 seconds as a final answer for part A, and I will substitute into my variable list the pre-rounded number just in case I'm going to use it in a future calculation. We are asked in part B to find how far the ball will be kicked from where it was kicked when it hits the ground. So we are looking for the displacement in the x-axis. Since we know velocity and time in the x-axis, and like I said, when we're dealing with the x-axis, we're always going to be using v equals d over t. I can solve for d because I know v and t. To get d by itself, I will multiply both sides by t. The t's will factor out, leaving d by itself. I can substitute my numbers in, so my time is 1.2331 seconds, and then our velocity, we said in the x-axis is 9.4 cos 40 degrees. It's all multiplication. Three sig figs multiplied by two significant figures gives me two significant figures, so 8.87935 meters is 8.9 meters. Part C, what is the maximum height of the ball? That means unlike in part A and B, the ball is not going all the way back to ground. It is only going halfway through its total flight path. So we will have to write a new variable list for part C because our final has changed. So in the x-axis, Vx remains the same because the ball travels at a constant speed in the x direction. The distance in the x direction, since the ball only went halfway through the process, will have to be divided by 2. And that's the same with time. We're only looking at half the total flight path, so the time has to be divided by 2. And that's true in both the x-axis and the y-axis. Acceleration is always 9.80 meters per second squared down. That does not change. Initial velocity, that's the speed with which the ball left the soccer player's foot. That does not change, but the final velocity does change because we are at the peak. The ball is no longer going up. It has not yet started going down, so our final velocity in the y direction is 0 meters per second. And the displacement in the y-axis, that's what we're looking for. The formula I'm going to use is Vf squared equals Vi squared plus 2AD. Since Vf squared equals 0, 0 squared equals 0, so I can eliminate Vf squared. So I now have 0 equals Vi squared plus 2AD. Next, I'm going to subtract Vi squared from both sides. And that gives me negative Vi squared equals 2AD. Now to get d by itself, I will divide both sides by 2a. The 2a's will factor out, and displacement has now been isolated. I can substitute my numbers in. Notice that I double bracketed the denominator because when I enter it into my calculator, I want to make sure that it divides by the product of 2 multiplied by 9.80. And that gives me negative 1.86266 meters. Two significant figures because of the 9.4 inside of the velocity. It's negative. I chose down as my positive direction. So negative 1.86266 is then positive 1.86266 meters up. And again, like we said, two significant figures. So my final answer is 1.9 meters up. A ball is hit off a cliff towards the green that is 30 meters below the cliff. If the ball's initial velocity is 25 meters per second, 50 degrees above the horizontal, how long is the ball in the air? I always start the same way. I write my variable list, and I always make the acceleration in the y-axis equal to 9.80 meters per second squared down. Now, the first thing I'm going to look at is how fast the ball was going when it got hit by the club. So our initial velocities. So the ball got hit and left with a speed of 25 meters per second, going 50 degrees above the horizontal. So when it was hit, it had a vertical and a horizontal component. 25 meters per second will be my hypotenuse, which means the velocity in the x-axis is our adjacent side, and the velocity in the y-axis will be our opposite side. So let's look at that adjacent side first, in the x-axis. Since that's the adjacent side, the value of that velocity will be 25 cos 50. So I'm going to put into my x-axis values, Vx is equal to 25 cos 50. The opposite side is the movement in the y-axis. That's how fast it initially, as soon as it was hit, that's how fast it was traveling in the y direction. And since it's the opposite side, its value is 25 sine 50. So in the y-axis for VIY, I'm going to write 25 sine 50 meters per second, and that is in the up direction. Now, what else am I given? I'm told that the green is 30 meters below the cliff. So when the ball lands, it'll be 30 meters below where it started. So in the y-axis, my displacement will be 30.0 meters down. And I'm asked how long is the ball in the air? So I'm looking for time. I do not know how far the ball will be displaced in the x direction. I do not know how fast the ball will be traveling in the downward direction when it hits the green. One thing I have to do in my variable list before I move on, I have to make sure that everything is facing the same direction. So in the y-axis, I have 2 downs and 1 up. So I'm going to switch everything to down. So my initial velocity in the y-axis will be switched from positive to negative, and the up will be changed to down. Right, so looking at what I have, acceleration, initial velocity, displacement, and time, I would be tempted to use displacement equals VIT plus half AT squared, since I know 3 of the 4 variables. Problem is, if I'm solving for time, that's going to give me a t squared term, t term, and non-t term. And nothing is going to factor out nicely, or I won't be able to get rid of any of the terms, which means I'm going to have to wind up going to the quadratic. So I'm a little too lazy for that. So instead of solving for time right off the top, I'm going to find final velocity. Then I'll look for time afterwards. I'm going to find final velocity using vf squared equals vi squared plus 2ad. So to get the final velocity, I will just have to square root both sides. And now final velocity has been isolated. I can substitute my numbers in. 25 sine 50 degrees squared gives me 366.765. 2 multiplied by 9.8 multiplied by 30 gives me 588. I'll add the two numbers together. That gives me 954.765. And square root of that gives me the plus or minus of 30.899 meters per second. Now I know logic dictates that this has to be down. The ball is going down when it hits the green. So of the two directions, I know final velocity must be 30.899 meters per second down. Before we go on, I want to point out that this is different than the example with the soccer ball. In the example with the soccer ball returned to its original position in the y-axis. The displacement in the y-axis was equal to 0. That meant the ball spent half its time going up and half its time going down. We were able to then conclude that the initial velocity was equal in magnitude but opposite in direction to what the final velocity was. Now note, in this example, initial velocity and final velocity are not equal in magnitude. That's because the ball spends more time going down than it does going up. That means that the final velocity is going to be larger than the initial velocity because the displacement is in the down direction. Now let's solve for time. I'm going to use acceleration equals change in velocity over time. I can use this because I know final and initial velocity, and change in velocity is always final subtract initial. To get time by itself, I have to get time into the numerator first, so I will multiply both sides by time. The times will factor out. That'll give me time multiplied by acceleration is VF subtract VI. Now to get time by itself, I will divide both sides by acceleration. The accelerations will factor out, and I have isolated time. Time equals VF subtract VI over A. Now let's sub those numbers in. First thing I'm going to do is deal with the 25 sine 50 degrees. When I punch that into my calculator, that gives me 19.151. Again, that is now positive because I was subtracting a negative. I will add 30.899 to 19.151, and that gives me 50.050. I divide that by 9.80. My calculator says 5.1072 seconds. Taking sig figs into account, my answer will be 5.1 seconds. Now I can add this time into my variable list, and I'm going to make sure I put it in as a pre-rounded number because I may use it for a future calculation. All right, B, how far will the ball travel horizontally before hitting the ground? So I'm looking at the x-axis and I'm looking for dx. I've got vx and t, and v equals d over t. If I'm looking for d, I'll have to isolate it by multiplying both sides by t. The t's factor out, d is equal to t multiplied by v. So we'll substitute numbers in. T is 5.1072 seconds, and Vx is equal to 25 cos 50 degrees. I'll just multiply the two numbers together. That gives me 82.0708 meters. So the ball has horizontally traveled 82 meters. And finally, with what velocity does the ball hit the ground? Well, the ball is coming in on an angle because it has a vertical component, which is equal to 30.899 meters per second down, and it also has a horizontal component, which is equal to 25 cos 50 meters per second, which is 16.06969 meters per second. So to find the velocity of VF, I'm going to have to use Pythagorean's theorem, a squared plus b squared equals c squared. So 30.899 squared plus 16.06969 squared. Add them together and then square root it. That gives you 34.828 meters per second. And we also need a direction. So I'm going to have to use tangent because this is a vector. And using opposite over adjacent and then inverse tan of that number gives me 62.5 degrees from the horizontal. And that brings us to the last lesson in the kinematics section. You're good to start the kinematics 3 assignment. It's found on page 8 of the handout.